Minutes past. Okay, you're recording. So last time um, we finished crystal structures. Today we are going to start with chapter 4, imperfections in solids. Why do we need to know about the imperfections in solids? Well, because the imperfections actually play a great role in characterizing the behavior of the material, specifically the metals. So you will see that these imperfections, which happen in the material either naturally or it could be manipulated as well, are reasons for why material are not all the reasons, are some of the reasons for why materials behave in that way. So we will see that towards the end of the lecture, of the end of the chapter, of course. So we will be talking about imperfections. What is the meaning of imperfection? Imperfections are interruptions in the material, you can call them. بالعربي نسميه خلل، عطب. So it's something which shows that you have something wrong in the arrangement of the material. And basically, there is no such a thing called a perfect crystal. Remember, we covered the crystal structures in the last chapter. We had the simple cubic, the body center cubic, the face center cubic, the hexagonal close back, and many others as well. And we dealt with the matter as if there is ideal crystal structures in the material. Now we need to understand that there is no such a thing called a perfect crystal. There are always imperfections happening in the material. على طول في imperfections موجودة. These imperfections are of different types. Most of the types we are going to deal with in this chapter. Imperfections also referred to as defects. Defect يعني عطب. Okay. Go for the laser. So it's also called defect. Defect does not also necessarily imply a bad thing, an evil thing happening in the material. On the contrary, in a lot of cases, what happens is that we introduce these defects deliberately. Deliberately, يعني عن قصد. We do it actually in order to impart certain properties of the material. For example, we add carbon to iron. Why do we do that? To make the steel. Why? In order to change the behavior of the material. It makes the steel much harder, much stronger. That's why we do it. But adding the carbon is a kind of imperfection that we are adding to the material. Addition of carbon to nickel or nickel to carbon. This system actually is very interesting system with unlimited solubility one into the other one. But anyways, we will deal that in chapter 9. We will take the phase diagram of this system. Addition of nickel to carbon, for example, we do that in order to make thermocouples. Thermocouples are tools which are used to measure, for example, molten metal temperature. So it's like a okay. It's like a thermometer, but it's not a thermometer. Of course, it's a thermocouple. It has a metallic wire which is immersed in the metal, and you measure the temperature there. You need actually why? So at the end of the day, why we are doing that? We are adding nickel to copper to raise the melting point temperature of the copper. Copper, you need in the thermocouple a good conductive material so that it conducts heat and therefore conducts the electricity as well to send the signal to the device which measures the temperature. But you need also this metal to have high melting point temperature. We add nickel to copper to raise the melting point temperature, and of course this causes the material to be stronger as well. But this is why we are adding nickel to copper, and that addition of nickel to copper, which we refer to as alloying, is an imperfection, is a defect that we are adding to the material. Nickel is not the same as copper. So it's an imperfection that we are doing deliberately in order to impart or to get certain properties of material. Addition of chromium to iron. This is also an addition to an imperfection. We do that mostly for corrosion resistance. For example, to make stainless steel is there, you want to make the iron corrosion resistant material. Also, introduction of grain boundaries to strengthen the material, and so on. So there are many things that we deliberately do in order to impart certain properties of the material. Now, grain boundaries, we have seen how materials develop, polycrystalline materials develop in the previous chapter, and grain boundaries are is a reason for why you could strengthen the material. For example, if you have a material with different grains there, okay, the material has different grain sizes, the more, suppose we have, this is a coarse microstructure, and in the other hand we have another microstructure which is much finer microstructure. Finer, yani the grains are much smaller there. So I'm trying to do a much smaller. I did not prepare that figure for this. I should have, not to waste time drawing just things like that. So anyways, you can see these are grains, and these grains are much smaller there, which we refer to as a finer microstructure there. So the microstructure here is much finer than the microstructure we have in the previous one. So you have much more grain sizes here than there. This is much finer, as you could see there. I'm trying to make them look, in a way or another, a much finer microstructure, which means finer, which means that it has much more, grains. Having much more grains means also they have much more grain boundaries. So why does that affect the material behavior? This is a fine microstructure. This is a coarse microstructure. The fineness of the microstructure affects the behavior of the material, and this is what I'm saying here. Introduction of grain boundaries. When you introduce more grain boundaries to the material, why are you doing that? In order to strengthen the material. How does this happen? Well, basically, this is what happens is that when you have fine microstructure, actually plastic deformation of the material happens due to what? Due to the movement of the large number of dislocations. This movement of large number of dislocation causes plastic deformation. The easier it is for the movement of the dislocation, the easier it is for the slip to happen, and the easier it will be for plastic deformation to happen. So the material will not resist the deformation. The material will behave low in strength. But if there is a lot of resistance to the dislocation movement, which means that a lot of resistance to the slip which can occur in the material, and therefore to plastic deformation, this means that the material will resist a lot, and this means that the material will be much stronger. Now, if the dislocation wants to move through this material, for example, it will be resisted by some imperfections, which are the grain boundaries, because the atoms here are arranged in this way. Now, suppose the atoms are arranged in this way, and the dislocation actually wants to move between these. The dislocation wants to move. That's the direction of the movement of the dislocation. It moves in this way. Of course, the atom is arranged in the same way in this grain all around. Once it reaches the grain boundary here, the arrangement of the atoms here are different. The atoms are arranged in a different way. The orientation of the atoms are different. This is what we have explained last time. So what happens there? Well, it needs to change its direction actually in order to move. It needs to go in this direction. So this grain boundaries actually present resistance to the dislocation movement, represents يعني مثل presents obstacle to the dislocation movement. Now, if a dislocation wants to move from here to there, let's say, there will be an obstacle here, an obstacle here, an obstacle here. So you have these obstacles here. This is in the fine coarse microstructure. Suppose you want the microstructure, suppose you want the dislocation, suppose you want the dislocation to move, yes, to move in the fine microstructure here. Suppose you want in the same area to move there, to move from here to there. You have much more resistances because you have much more grain boundaries. Each grain boundary it faces, it presents an obstacle. So you have much more resistance to the dislocation movement, and therefore the much more resistance of dislocation movement, which means that much more resistance to slip and much more resistance to plastic deformation. So therefore the material will behave much harder and much stronger here. Fine microstructures are much stronger than the coarse microstructures. This is a brief explanation to what I'm saying. Introduction of grain boundaries. Normally we can reduce or increase the grain boundary area in the material in order to control the strength of the material. And these grain boundaries are actually imperfections also in the material. So this is what we are doing. Defect in general simply refers to what? It refers to a disruption in the crystalline order of a periodic material. You have a disruption, grain boundary is one, of course. This is what imperfections of materials are. Now we have several types of imperfections there. We have the point imperfections, we have the line imperfections, and we have the area imperfections. These are the most important ones. Of course, we have others. At the end of the chapter, we will be looking at the others as well. The point imperfections like the vacancy atoms, the interstitial atoms, and the substitutional atoms. This is an interstitial atom, which we are showing here. This is a substitutional atom. The vacancies we will show on the next slide. And line defects like the dislocations. The dislocations are examples of dislocations. Dislocations are examples of line defects. We will see them, of course. And the third type will be the area defects, like examples of those are the grain boundaries. You write it yourself. Okay. Now to start with the first type, which are the point defects. Actually, we have the vacancies and the self-interstitials. What are the vacancies? Actually, in the material, you can see that you have a vacant atom in the lattice position. In this position, there should be an atom, but it is missing. This missing atom is called a vacancy. All crystals contain some vacancies in them. You cannot have a material, solid crystal, without any vacancies. They will be always there. Now, what does this vacancy, that's important to know. What does that vacancy actually do to the material? What it does is that it causes a kind of stress in the vicinity of this vacancy, as if you have a tension load here in the vicinity of the vacant atom. And so that is number one, as if it is causing a tension load. In addition to that, it causes also change in the behavior of the material. How is that? Now, suppose the dislocation, let's say, is here. Let's take this part, which is perfect. And suppose the dislocation wants to move in this direction. Basically, what happens? The material will be under a shear stress. So the movement of the atoms in this way or the other way, it is simple, and that is also a close back direction. These are touching one another. You don't have much a problem here, so the dislocation moves normally. But on the other hand, the place where you have a vacancy there, you have a problem. Suppose the dislocation wants to move in this direction now, and there is a load in this direction. So what is going to happen there? You see, this atom will be resisting the movement, either this way or that way, will be resisting the movement. This atom and that atom will be, will be opposing the movement of each other, which causes resistance to the movement of the dislocation, as you could see. So this resistance to the movement of dislocation means that you have to apply more load in order to make it move. So this is where the effect of the vacancy atom comes there. So that is one. And another thing, as we said, as if there is a tensile stress, internal tensile stress, residual tensile stress in the material in the vicinity of the vacancies. So that's important to notice, because when we explain then how the dislocation moves, maybe at the beginning of next lecture, it's important to realize that. That is one type, which are the vacancies. The second type of the point imperfections are called the self-interstitials. And instead of having a vacancy like that, actually you have one extra atom. The atom which escaped from here. Of course, atoms would escape from a place because they have enough energy to break out from here and to run away, to go somewhere else. Maybe it came here. Okay, so that's called the activation energy. To have enough energy to be able to escape that bonding which is there is called the activation energy for vacancies. Now, on the other hand, we have self-interstitials, as if you have an extra atom squeezed in between the lattice atoms there. So this actually atom is squeezed, as you could see there, and it causes also problems. The same way the dislocations want to move in this area, it will have difficulty because this atom will be resisting the movement of the dislocation in different directions there. That's number one. And number two is that in the vicinity of the dislocation here, you have another kind of stress developing, which is a compressive stress, an internal residual compressive stress in the material, which is not there, for example. It's not here, but it is only here. And that's important, as we said, in the development of how the mechanics and the mechanics of how dislocations actually move, which we will explain next time. The self-interstitial atoms are less common. Simply, they don't happen as much as the vacancies here, because it requires much more energy in order to squeeze in between atoms, rather than much lesser energy, which it requires only the activation energy to develop a vacancy in the material. So this is one type, which are the point defects. The vacancies, as we already explained, they require activation energy in order to form a vacancy. Vacancies are also a function of the temperature of the material. The higher the temperature, actually, you can see that from this equation, the higher the temperature, NV is equal to N naught exponential to the power with a negative sign, and you have the T here. So this means when you increase the temperature of the material, you have much more vacancies developing in the material. So why? Because when you raise the temperature, you give more energy to the atoms, basically, and they can move faster. So if they are there to move to their condition prevails moving out, so they have enough activation energy to do that. Now, going back to impurities in solids, it is impossible to have 100% pure materials, basically. So that is when we are talking about point defects there. So addition of alloying elements is considered one of the impurities added. So impurity or foreign atoms are always present in the material. Even when we have 99.99999% pure material, still we will have 1 times 10 to the 22 to 1 times 10 to the 23 impurity atoms in every cubic meter of material. In an alloy, as we have already said, the impurity atoms are added intentionally, yani deliberately added, in order to impart the specific characteristics of the material, such as improved material strength and corrosion resistance. These are just examples I'm citing here. Now, addition of those alloying elements, impurity atoms, whatever you want to call it, it develops what we refer to as, or causes the formation of what we refer to as the solid solution. What is a solid solution? So we have a solid solution forming. What is a solid solution? What is a solid solution? Keep. Sorry guys, I had to answer this. So we are already recording here as well. Okay. All right. So we said, what is a solid solution? Solid solution, let us explain it in this way. A solid solution is a compositionally homogeneous material, solid. Actually, impurity atoms are randomly and uniformly dispersed in the material. يعني بشكل عشوائي و randomly dispersed in the material. Like what I already said here, just like a liquid solution. But in this case, we have a solid solution. What's the difference between a solid solution and a liquid solution? Well, in order to make things clear, yani easy, in a liquid solution, the difference is that if you have, for example, water or tea that you're making, you add sugar to it. What happens to this sugar is that the sugar is going to dissolve in the material. So this sugar will not show up because it's going to dissolve. Dissolve, they become very, very small. They go behind the molecules of water. You cannot see them anymore. So the water can accommodate that amount of sugar. So if you add more sugar to that, what is going to happen? Well, it's again going to dissolve. If you add more of the sugar, well, it's going to dissolve up to a certain limit, a certain concentration, up to a certain concentration there. Then what's going to happen? The water or the tea will not be able to accommodate the sugar in it. So what's going to happen? It's going to precipitate at the bottom here. The sugar is going to precipitate. That concentration is we refer to as the solubility limit of the material, of the liquid. Now, for the solid, we have the same thing. Of course, the solid has to be in molten condition, molten يعني سائل, in order to mix the alloys together. So the same thing happens to the solid as well, except that the solid has to be, first of all, in the molten condition. You mix up the alloys or mix or add the alloying elements to it, the impurity atoms are randomly and uniformly dispersed within the solid, and then they solidify. And as they solidify, if they don't reach the solubility limit like what we have in the sugar here, it is going to be a solid solution. But once you reach that condition where you have the solubility limit is reached up to a certain concentration there, what is going to happen? It's not going to, of course, precipitate here. It's going to form a new structure, a new phase in the material. That's the difference between solid solution and liquid solution. So in the liquid solution, precipitation is going to happen. In the solid solution, the addition of the impurity atoms results in the formation of a new phase if that concentration is more than that concentration is added to the material. If the solubility limit is reached and beyond the solubility limit, then the formation of a new phase is going to happen. Definitions are in the same way as we did for the solid solution. We have the solvent, which are the host atoms, يعني المضيف, elements which are compound present in the greatest amount, and the solutes are the impurity atoms or the alloying elements if you want, which are the elements or compounds which are present in the minor quantities there. We have basically two types of solid solution. We have substitutional solid solution, like in the case of the copper and nickel. You have now here, you have solid solution basically forming because you did not exceed the solubility limit, the concentration, the maximum concentration the material can handle. The material here, the mother material here can dissolve, let's say, more up to a certain limit of the copper. The nickel can accommodate copper atoms there, but up to a certain limit. Beyond that certain limit, you can see it will form another phase, which we refer to as the second phase, which can develop in the material. This second phase has a different composition, and often it has a different crystal structure as well. And behavior of this material is also different than the rest of the material. So this is one type of the substitution of the solid solution, and the other type of the substitution and solid solution, of the solid solution, we refer to as the interstitial solid solution. You see, interstitial comes from the spaces between the atoms. You remember that every crystal structure, we calculated the atomic packing factor, so it's not 100% occupied. So you have vacancies inside between the atoms. These atoms can go in those interstitial spaces. As you can see, this is an example there, and this is another example. In this case, we have the carbon in the iron, for example. Carbon is an interstitial atom which can develop an interstitial solid solution there. What does the carbon do? It does a lot of things there, of course, when it goes in the interstitial atoms. It does not bond with the iron, but it does something else, which we will be seeing later. So these are the types of the solid solutions. Of course, solid solution is one type of point imperfections, which we are already talking about. And the presence of the solid solution or otherwise development of second phase particles depends on some conditions. For example, and this is what I'm saying, either if you have a solid solution, substitutional or interstitial, there are conditions to form this or that, or development of the second phase particle. So first of all, in order to form a solid solution, the atomic size factor needs to be the same. In the substitutional, the solute atoms need to be close to the solvent atoms which we have here in terms of atomic size. If it is very different, then it cannot form a substitutional one. In the interstitial one, the size of the atom which you have, in this case carbon, has to be much smaller than the iron atoms there in order to be able to be accommodated in the interstitial spaces. So these are conditions for the formation of solid solution. Another condition is the crystal structure. Yani you cannot bring and form a substitution of solid solution, for example, and this condition is for the substitution solid solution, you cannot bring an atom there which displays a different crystal structure and say you will make a solid solution with this atom which has a different crystal structure. Say, for example, if this makes a BCC crystal structure, for example, and this normally forms an FCC crystal structure at the same conditions there. You cannot form a solid solution. Why? Because this atom wants to make a FCC. When it reaches here to the material, put it there, he will say, okay, let's go guys and make an FCC crystal structure. The atoms, the host atoms, and the big part of the atoms there would say, no, my goodness, where are you coming from? We are only making BCC crystal structure, go away. So not a solid solution cannot be formed. So crystal structure is a condition where the solute atoms, where is that? The solute, my goodness, the solute atoms, by mistake, solute atoms need to have the same crystal structure as the host atoms there, the solvent atoms. Another condition is the electronegativity and the valence. Actually, these two conditions show or represent actually the energy which the material has. The electronegativity should be the same. The higher valency, higher chances of solid solution formation. So these are conditions. These actually prevail, or these actually represent the energy of the atom. Let me explain it in this way. When you bring an atom there, for example, and wanted to go up and make a solid solution, so that it actually, when you are putting a substitutional atom here, what does the word substitutional mean? Substitutional means it substitutes, يعني ياخذ مكان. It substitutes this atom. An atom like this should be here, but it's going to substitute it. Yeah, like for example, if there is a manager working in a company, and that manager has a problem, he was sick or he wanted to go on a leave, vacation, then he will be substituted by another person who can do the same job, who has the capability of doing the manager's job. So this is what's done there. This substitutes an atom, or the copper substitutes an atom of nickel, and it can do the job of the nickel. It has the same crystal structure, it has the same, nearly the same dimensions, not the same dimensions exactly. It has also the same energy actually, because suppose this had much higher energy than this, it cannot be there. Like imagine you have in the nursery kids which are sitting in the class, and they are all quiet and very very quiet and nice, and you bring a guy with them in the class who is very naughty, he moves a lot, he cannot sit in the chair for 2 minutes, so he cannot be accommodated well in this part as well. So this is just to bring things simply. Electronegativity, which is ability of the material to attract electrons basically, or valencies, have to be also very similar, not exactly the same, have to be similar in order to form a solid solution, and most of the conditions are for the substitution in solid solution. If these conditions are available, then obviously you will be forming a solid solution. If not, then normally a second phase particle or second phase is going to develop in the material. The third, this is now we talked about the up until now we talked about the point imperfections. The second type of the imperfections are called the line defects there. And what are the examples of line defects? Are the dislocations. Dislocations result from solidification of a melt. This is one way. When you are solidifying any melt, and normally when we heat or treat the material, when we make it molten metal, دوبة, بعدين we solidify it, dislocations are going to form in the material. Not only because of that, but also due to the mechanical working. Any mechanical working you perform on the material, such as rolling, drawing, compressive impact, tensile, or shear stresses, any straining, plastic deformation that you cause to the material, again, imperfections are going to form in the material. Or from thermal stresses. If there are thermal stresses due to the heating of the material becomes bigger, so it causes thermal stresses in the material. Again, dislocations are going to form in the material. It is very difficult to form a dislocation-free crystal. You cannot have any crystal without dislocations happening in them. So dislocations are inevitable. You always have dislocations in the material. We already learned that dislocations make metals weaker than they should be. Why? Because the dislocations, actually movement, causes the slip in the material. Without the dislocations being there in the material, the slip in the material would not be possible. And therefore, plastic deformation in the way that is happening there would be very difficult to happen as well. So therefore, the material will behave very hard and very stiff. So the availability of the dislocation enables the material to easily plastically deform. But also this causes that it allows the metal to be deformed. It allows plastic deformation. So what causes the plastic deformation is the slip which happens in the material, which is caused by the dislocation movement. Without the dislocations, no plastic deformation would be easily possible in the material. And we will see that in the next lecture, that without the dislocations, you would have to spend, if you wanted to deform the material, you would have had to spend more than 100 times the force or the stress that you are applying now in order to plastically deform the material. We will see why that's not the case in what we have. So in the deformation, before deformation, we are showing the material, and after deformation, the slip actually occurs in the material. The dislocation causes the slip between the crystal planes when they move. When the dislocations move, they cause the slip, and therefore they allow plastic deformation to occur in the material. Now, the dislocations are of two types. We have the edge dislocation and we have the screw dislocations. Let's look at them. The edge dislocation, think of the edge dislocation as if you are, let me make this bigger, all right, think of the dislocation as an extra plane, like in this one. Suppose if this is not there, actually, you are looking only at this. This is a perfect crystal, as you could see. Oh. But the imperfection is that there is a half a plane, as you could see here, as if it is immersed in the material and is squeezed in the material. This half plane is inserted within the crystal structure that you have here, which is causing an imperfection in the material. This is how an edge dislocation basically looks like. Misalignment of atomic plane, as you could see, this misalignment, it's misaligned, and this is misaligned, this is misaligned. This misalignment of a plane is caused by this extra half a plane in the material. This is what we refer to as the edge dislocation. And the other type we refer to as the screw dislocation. It looks a bit different. Imagine you have the crystal perfect here, and then you cut in between half the plane all through, and then you move the position of one atom, one unit cell further down, and therefore the bonds which were between this and that are not there. It's between this and this, and between this and this is between the one here and the rest. So that actually is another type of imperfection happening in the material. The bonds move from one to the other one as if you are screwing in the material like that, and that is why we call it a screw dislocation, basically, from the way it looks like. Now, this is what we refer to line imperfection, which are the dislocation. We will use what we learned here next lecture to explain how and why plastic deformation happens again using the knowledge of the dislocation. But for now, let us continue with the other kinds of the dislocation of the imperfections. The last part are the area imperfections, like what happens in the polycrystalline materials. Most materials are polycrystalline and are made from many single crystals, which we have dealt with last chapter. So what happens there when the molten metal, we have a molten metal, when we cool it down, due to the gradient of temperature across the material, the solid crystal nucleates in different positions at different orientations. So this is why I'm saying during solidification, the solid crystal nucleate and grow from the liquid in random orientations. They grow, they nucleate here, and then they grow. And they grow in different orientations there. The grains impinge, once they become bigger and bigger, they impinge against each other. So this is what I'm saying. The grains impinge on each other when the solidification is complete. The junction between the grains there are called the grain boundaries. There is this mismatch between one grain and the other one in terms of the atom orientation causes the development of the grain boundaries here. So the grain boundaries basically occurs due to the crystallographic mismatch when two grains are meeting. So when you have a grain and another grain, there is a mismatch between them. The orientation here is in this direction. The orientation here is in this direction. Due to the mismatch between them, this grain boundary is going to form. They are categorized also with, when the mismatch orientation is large, we refer to it as high angle grain boundary, as you can see here. The mismatch, if you draw a line like this, so in the direction of the orientation of the atoms here, and another line in the direction of the orientation of the atoms in this way, the angle between the two, when it is large, it's called high angle grain boundary. But for example, here you can see that the orientation of atoms are in this direction, and this one it's in this direction. The difference is not much. If you draw a line like that, and then another line in the orientation of these, you will see the angle between them is small, and this is called low angle grain boundary. One important thing that we need to understand here is that at the grain boundaries are imperfections. The atoms at the grain boundary, as you could see there, because of the mismatch, as we have called it there in the previous one, because of the mismatch between them, because of the mismatch between the grains there, they are less bonded. As you could see, you have more vacancies at the grain boundary there as well. The atoms are less bonded there. So atoms are less bonded, and atomic packing is lower than the grain itself. We refer to that low coordination. So here within the grain, the atoms are bonded perfectly, but within the grain boundary, the atoms are not well bonded altogether, and you have vacancies happening in the material. So what does that result in? It results in that you have a difference in the energy between within the grain here and the grain boundary. Why? Because, and that is called the interfacial surface energy difference. That is what I'm saying, the interfacial surface energy or grain boundary energy. That is interface between a grain and another grain. There, the atoms here in the grain boundary area are more energetic than the atoms within the grain. Why? Because the atoms within the grain are well bonded, while the atoms at the grain boundary are not well bonded. So they need to bond in order to be stable. So they are more energetic. So this is why we say the energy at the grain boundary is more than the energy within the grain. Grain boundaries are more chemically reactive in the case of solidification. at the out, like in the case of the solidification. يعني when you have that is, I don't know why it's not shown here, but if you have a droplet of water, for example, or you have some material like in the outer. Let's compare this to rusting or corrosion. Why does the corrosion occur in the material? Basically, the outer surface of the material, if this is the outer, the atoms are there. Okay, the atoms are there in the outer surface of the material, and I'll do that fast. And the atoms there within the material. These atoms within the material, let's say, are bonded very well, but the atoms at the surface of the material are not bonded very well. They lack bonding. So what do? They react with the environment in order to complete their electrons or whatever, in order to, to gain stability. So this is why they bond with the environment. For example, they corrode. Iron, for example, it corrodes when it is allowed to do that. So that is what does it do? What does it do? It's going to react with something. That is reaction. They are more energetic. Here we have it inside the material. Actually, it is more energetic, although it is inside the material, but due to the formation of the grain boundary, the atoms are not bonded together very well like the grain boundary, and that's why they will be more energetic than within the material there. Last slide that we are going to look at. There are low angle grain boundaries, which we normally describe as an array of dislocations. These are called the tilt boundary and the twist boundary, but normally I don't like to categorize them in this way. They normally call them the edge and the screw. The grain boundaries actually either low angle or high angle. They cannot be compared to the dislocations. They are different completely. Some books do that. We also have the last types, which are called the bulk and the volume defects there. We dealt with point imperfections like vacancies and self-interstitials. We dealt with line imperfections, which are the dislocations. We dealt with area imperfections, which are the grain boundaries. But we have volume or bulk imperfections also, like the pores, yani voids in the material. These are also imperfections. Cracks you could have in the material. Foreign particles you could have in the material as well. These are all imperfections that can happen in the material. We have something called the twinning, like you have a twin like this happening in the crystal structure, yani like a mirror basically. One like this, the crystal structure goes like this and comes back like this. Is a twinning, which is an imperfection. Stacking faults. Remember in the FCC and HCP crystal structure, we said we have stacking faults. Like in the hexagonal close pack, we said we have the A, B, it continues like that, A, B, like that, and it continues in that way. This is called the stacking sequence. But you could have a fault there like that. You have A, B, بعدين يروح B, A, B مرة ثانية. So that is called the stacking sequence. Like in the FCC crystal structure, we had the A, B, and C instead. Actually, there we have A, B only. A, B, C. Then you have A, B, C, like that in the material, the crystal structure. So you could have A, B, C, and then it starts to say A, B, and then again it goes to A, B, C. So that is also a stacking a fault, or we call it a stacking fault in the material also. Another last type of imperfections also we refer to as the phase boundaries. Like if you have the grain boundaries are imperfections, of course, but you could have another phase also forming in the material, a different phase, which have a different crystal structure there. The boundary between it, that boundary between it, this phase, and the rest is called second phase boundary. That second phase boundary, also very similar to the grain boundary, plays a role into changing the crystal structure, and it is an imperfection happening in the material. I'm done today. We will talk. Sorry for taking a little bit more time. Let me stop the recording. I will keep that. Any questions, guys? Any questions?